Hello, welcome. I am going to hopefully do several examples of computing some non-trivial K-moduli spaces today and sort of inform some of the general theory of how you might approach these kind of problems along the way. So I put kind of a generic statement of the K-moduli theorem at the top of the board. So we have this is what we talked about last time. We have this thing, the Artin stack and its associated good moduli space that give us a suitable parameter space for K semi-stable and K polystable varieties. The next question that one might ask, I mean, some people might be perfectly content with this, but what we want to explore today is how you might actually find what these are. If somebody hands you an N and a V, what are going to be parameterized by these moduli spaces? Right? The question that a lot of people currently are thinking about, or even for Fano threefolds, for a family of Fano threefolds where a generic fiber is K semi-stable, are all of the smooth members also K semi-stable? So I mean, trying to understand even just the smooth part of these moduli spaces is quite non-trivial. But one thing I wanted to point out that was brought to my attention afterward, based on, I wrote a formula on the board, and then I concluded some inequalities, which did not follow from the formula that I wrote, because the formula I wrote, I did not include the N. So for those of you who've seen this before, I think you all just wrote the N, but just made a typo on Tuesday's lecture. The formula, including the, for relating the total global volume to the normalized volume, is this. The volume of your semi-stable Fano is bounded above by 1 plus 1 over n to the nth power times the normalized volume. So this n was missing in the formula, but the conclusions were stated correctly. So just if you are looking at your notes and you wonder how we got 9 over 2 instead of 3 over 2, it's because there was an n that was missing. So like I said, what I'd like to do today is a few examples of finding more involved K-moduli spaces and hopefully discuss a couple of theorems along the way. So does anyone have any questions, comments before we start? We just start? We just start, maybe? So a couple of, I don't know, just, maybe let's just start with an example and see what happens. So what we did last time, at least for P1 and P2, we could compute the whole K-moduli stack and the moduli space. And both of these were just a point. And perhaps you may want to try to generalize this for all Pn and see what you get, especially after we had Tiago's exercise session talking about computing K-stability using some deltas. So you can show that Pn itself is K polystable. So maybe as an exercise, you could try to show Pn is K polystable. And it is also, I mean, by some sort of, classical results, it is the only Fano variety, the only smooth Fano with this maximal volume. So you could say the same statement holds for Pn. Okay, so maybe as an exercise if you want to think about the Pn case. But what I'd like to do today is think about more surface examples. So the first or a nice example that illustrates the framework I want to present is a case of cubic surfaces. So maybe let's start there. So what I want to consider is in the K-moduli space of dimension 2 and volume 3, I want to consider one component of this moduli stack or moduli space that parameterizes just the smoothable elements. So I want to consider in here, maybe I'll call this SM23, which this is the component parameterizing what we say Q-Gorenstein smoothable del Pezzo surfaces, so maybe I'll just say Fano surfaces with minus kx squared equal to 3. And so what does Q-Gorenstein mean? Q-Gorenstein is built into this Kolar condition, this extra condition we were putting in the stack. For now, it just means Q-Gorenstein smoothable. There exists, maybe I'll call my Fano surface X. So we can say there exists some family, maybe curly X over T, where one fiber is this Roman X, and the generic fiber is smooth, and the relative canonical divisor, the Q-Gorenstein condition is the relative canonical divisor is Q Cartier. So these are the objects that we are considering in this moduli problem. We're only considering Q-Gorenstein smoothable. I mean, the Kolar condition is like strictly stronger than that over certain bases, but you can think of the Kolar condition as being just saying the relative canonical divisor is Q Cartier. And these are the objects we want to parameterize. And I only want to talk about the smoothable ones. Actually, the non-smoothable ones, I was talking, if you have a good example of a non-smoothable Fano surface with anticanonical volume 3, let me know. I was trying to make one yesterday, and I think maybe they exist. But I don't know if they're K-semi-stable. So anyway, we're just going to talk about the component where I can say something. So the moduli space might have many pieces, and we're going to talk about one piece. So what is this component? What is going on here? Well, what one can prove, it turns out, maybe the theorem, this is, I guess, originally due to Odaka, Spati, Sun, that K, either poly or semi-stability, of a cubic surface is equal to the notion of GIT, poly or semi-stability for the cubic. And in fact, this is maybe one version of this equality, and namely what is true is that this component, the smoothable MSM23, this K moduli space is actually isomorphic to the GIT moduli space of cubics. And if you've seen GIT before, right, this is, you take the parameter space of cubics, take the parameter space of cubics. Oh, P3, yeah, thank you. Thank you, P3. We're not talking about curves, we're talking about surfaces here. You take the parameter space of cubics, and you take the GIT quotient by, oops, my gosh, PGL. We're working in P3, so PGL4. So if you're not familiar with GIT, I'm going to illustrate some notions of GIT here. But K-stability is something that we have all of these test configurations, all of these invariants, all of these things to compute in at least low dimensional and low degree examples. GIT is something that we can compute in, like, we just know what surfaces are GIT semi-stable. There's a numerical criteria for determining what's parameterized by these things. So this is an example of how we can relate a K moduli space to another moduli space, and then we know everything. So in particular, these kind of results will tell us exactly what objects, I wrote this for the moduli spaces, this is also true for the stacks, but this will tell us exactly what objects our K moduli space parameterizes because this side is known. Okay. So how do you prove something like this? Also, for those of you in the audience that are more familiar with this, this is known in higher dimensions, and it's conjectured in every dimension. But there is sort of, the proof in every dimension will follow the same argument, but there's one thing that is conjectural in dimension at least 4. But this is conjectured to be true that if replace surface with hypersurface, the same thing holds. We'll get to it in just a second. Yeah, it's related to this. Yeah. So if one could prove the gap conjecture, then you have this. Okay, but let's try to talk about how you prove this with our first example of today. And the idea, if you are familiar with GIT, is somewhat straightforward. We have K-moduli, which we've used a lot of invariants for, right? We have the delta invariant, we have the Futaki invariant, we have we have all of these things. But the Futaki invariant looks like one-parameter subgroups, which is what you use to detect GIT. Okay, so in maybe we'll say, just as a little background here, K-stability. We have test configurations. So test configurations were what Hamid talked about on the very first day. So you have some x, which you want to know if it's K-semi-stable or not, and you associate to x a test configuration. So this x, this curly x over A1, such that this is trivial away from 0. Right? So we have our test configuration, and to the data of a test configuration, so this is a family over A1, where the generic fiber is what you started with. And to this, we associate the Futaki invariant of this test configuration. And to be K-semi-stable, we wanted this to be greater than or equal to 0. There was some numerical invariant associated to this one-parameter family of varieties that we could determine K-stability with. With GIT, you have what are called one-parameter subgroups. But the construction is very similar. Okay? So one-parameter subgroups, at least in this case, if I'm looking at GIT of a projective hypersurface, so maybe we have some x inside Pn, we take what usually is denoted by lambda, a one-parameter subgroup inside the automorphism group of Pn. So usually this is a diagonal matrix. So usually this is a matrix that's acting on the elements x. And you take this is a one-parameter subgroup, and you take the limit as, I don't know, lambda. Okay, maybe I should call this lambda as, I don't know, the diagonal. You take a limit as lambda acts on the class of x maybe I'll call this x0, is the limit of lambda acting on x. So lambda is a one-parameter subgroup, so maybe lambda depends on t. I'm going to take the limit as t goes to 0 of lambda acting on x in the Hilbert scheme of Pn. So this is what is usually sort of set up. But what is this? If t is your parameter for A1, this says for a generic t not equal to 0, you've acted on x by an automorphism. So x, it's isomorphic. Okay? So you have a copy of x over some fiber t not equal to 0. And over t equals 0, something has happened, right? You've possibly gone, you've taken a limit, and maybe lambda has degenerated x to something else, to some x0 in the Hilbert scheme, and you might get something that is x0 that is not isomorphic to x. But this is a test configuration, right? This is a family x over A1. But it's a special family, x over A1, where the central fiber is in that same Pn. The central fiber is the limit in the Hilbert scheme. So x0 is still inside the same Pn. But in any case, this is a test configuration. In GIT, you associate a numerical invariant to this data, the Hilbert-Mumford weight of lambda. And being GIT semi-stable, so this was the K semi-stable definition, being GIT semi-stable is if, well, depending on your GIT conventions, where this is greater than or equal to 0. So this is some appropriate numerical invariant, the Hilbert-Mumford weight. And this being greater than or equal to 0 is what it means to be GIT semi-stable. But looking at these two pictures, right, I mean, this is in fact a special case of that. In this case, the family over A1, the generic fiber is X. You have no control of the central fiber, right? The X0 could be in some other space. There's no reason the X0, if X lives inside Pn, the central fiber of this does not have to live inside Pn. So this is somehow more general, but this is at least a special case of that. So you might expect a relationship between these two invariants, and in fact, that's true. Okay? So this is a general idea due to Paul and Tian. So maybe we'll call this, I don't know, a theorem or a proposition, or call it a theorem. Well, the idea comes from Paul and Tian that says K stability implies GIT stability for hypersurfaces. I mean, this is actually, there's more general things you can say here, but I'm going to say, I'll just say it in this way. And the proof of this is very, the proof of this is just this. I mean, there's some numerical calculation of what these invariants are, but the proof is let lambda be a one-parameter subgroup in the GIT case, and let maybe x sub lambda be the associated test configuration. Then it turns out the Hilbert-Mumford weight of this particular lambda with the linearization O1 coming from Pn is equal to a constant times the Futaki invariant of this test configuration. And the crucial part is that the constant is positive. Okay. So if the Futaki invariant is greater than or equal to 0, the Hilbert-Mumford weight is greater than or equal to 0. So there's some computation here, right? I mean, to compute the Futaki invariant, there are these formulas that you have to use, and you have to know what the Hilbert-Mumford weight is in order to justify this, but this is a computation that one can do. And so this is true in generality, and what you would want to do to go the other direction is hope that somehow you can reverse this. But you can't reverse this even though the Hilbert-Mumford weight is a multiple of this test configuration. Just knowing the Hilbert-Mumford weight is non-negative does not imply that the Futaki invariant of every test configuration is non-negative, because test configurations are these more general objects where we possibly have to degenerate X outside of Pn. So this is only a one-way implication, but in many cases, it's an if and only if, like in the case of cubics. So that's, first of all, I mean, this is the first indication that K stability is often related to GIT, which is nice. You know, if you have something that is GIT unstable, it has to be K unstable. It's a useful criteria. But yeah, how do we go the other direction? So let's do that for cubics, and then talk about some more general examples where, aha, here they are. Yeah, or how you do this. If it's not an if and only if. I didn't really explain what GIT is, so if you haven't seen it, I apologize. But if you have not seen GIT, just think of it as a version of K stability at the moment, for better or worse. Yeah, I'm bringing the board down. Do there have questions? Yeah?
How would you define the Hilbert-Mumford weight in the case that we have?
In the case of what?
Yeah. How would you define the Hilbert-Mumford weight?
So typically, what the easiest definition one can take, usually we take this to be these are matrices, right? So we diagonalize this, and you have a matrix, and so you have a matrix that's diagonal, and up to some coordinate change is just powers of t. So on each coordinate in Pn, it is acted upon by some power of t. So if you have, maybe if you have a matrix that's, well, let's sneak this in right here. Like if I have a matrix t to the a, t to the b, t to the c, something like this, a diagonal matrix, this will act on any monomial, or so therefore any hypersurface in Pn. So maybe acts on a hypersurface like x squared plus y squared this is not a cubic, but whatever, right? It acts on this by just plugging in. So you get 2 to the 2a x squared plus 2 to the 2b y squared. Well, I don't know why I picked a long equation, but whatever. 2 to the 2cz squared. And the Hilbert-Mumford weight is okay, by my convention that I've defined it, you look at the minimum over all of the coefficients of the monomials.
Maybe I should rephrase my question because I know how to define it this case. So what is the line boundary?
So I'm choosing O1. Yeah, yeah.
No, because we're in the Hilbert scheme now, not in the Hilbert case. I'm asking about the Hilbert scheme.
So I mean, in this case, I'm doing all of this in the case that X is a hypersurface in Pn. Yeah, yes. You can do this more generally, but you have to be careful. Yes, okay. So in the complete intersection case, you can get a relationship this way. But ultimately, if you want this coincidence between the, this is maybe a cop-out answer, but between the Hilbert-Mumford weight and the Futaki invariant, you need the line bundle you're using here to be at least proportional to the CM line bundle in your family. So the CM line bundle comes from this sort of relative canonical divisor on any family. And so you, in order to get this inequality, you have to have this be a multiple of that. So yes, there. No. Okay. Oh yeah, I was bringing the board down. Bringing the board down. Other questions? Okay. How do we go the other way? How do we do this for cubics? So how do we prove the theorem of Odaka-Spotty-Sun? Let's say X is a cubic surface. And we want to try to go the other direction. Okay? So let's assume X is a cubic surface in P3. We want to show that GIT stability implies K stability. Okay. So we have a general statement that goes the other way for any hypersurface, but here, let's see why we need special cases for this to be true. If we have a cubic surface, well, maybe this is step 0. Step 0, there exists a K stable, or maybe K polystable, K semi-stable, I don't know, K whatever stable you want, K semi-stable cubic surface. So the moduli space I'm talking about is not empty. Okay, I mean, we need something like this to be true. There exists a K semi-stable cubic surface, and you talked a little bit in, I think, Tiago's exercise session about the toric criteria for showing certain things are K stable. So for example, you can write down this cubic surface. You can either use the fact that it has a large automorphism group or that it's toric or whatever you want to conclude this one is K semi-stable. And so that tells me the generic, because K semi-stability is an open condition, right? The generic cubic surface is in fact K stable. It has a finite automorphism group. So it's in fact K stable by openness of K stability. Okay. So first of all, I mean, this is maybe step 0 of our moduli problem, is just the K moduli space is not empty, and it at least is going to contain the generic cubic surface. So that's our starting point. But how do we do this? So I said let X be a cubic surface in P3. What example? This? What's wrong with this example? I mean, it's polystable. Semi-stable is. I wrote K-stable. Yeah, so I should say polystable because then so you have to use it also has finite automorphism group. I mean, you have. Oh, yeah, okay, sorry. You just want me to write polystable here. This is what you're saying.
Seriously.
Yeah, okay. Okay, I mean, sure. Yeah, I mean, you can find one. Yes, I mean, okay, so yes, I agree with the point. I agree with the point that's being made. This one that I have written down is polystable. Yes. Okay, so this one I've written down is polystable. So using openness of K semi-stability, we only conclude the generic fiber is K semi-stable. Yes. If you find one that is actually K stable, then you can conclude the generic one as K stable, which is also true. But I was trying to use this one that we were discussing the other day. So. Anyway, it is still true that the generic one is K stable. But maybe I should say there exists a K stable, but then you have to change the hypothesis here. Yes, sorry.
And is this property of openness hard to see, or?
Yeah, so openness is one of the crucial things that we were talking about on Tuesday. To prove, I guess the current proofs, I don't know, the proofs by Bloom, Liu, and Xu of openness they prove that the delta invariant, or at least the minimum of the delta invariant in one, is a constructible function. So, I mean, this is a very non-trivial result. But this is one of the things we needed to define the stack anyway, and show it has a good moduli space. So, it's true. But it's a hard result. Other questions, though. Sorry for unintentionally confusing the audience with my example and the conclusion that did not follow from the example that I wrote. Other questions? Okay. So once you have the existence of a K semi-stable cubic surface, well, at least we know the moduli space is unempty, and then if you pick not this surface, if you pick a different one, you can in fact conclude it as K stable. But the semi is needed with this example. But nonetheless, how do we do this moduli problem? How do we get back to this? So we have a cubic surface in P3. If we want to show GIT stability implies K stability, let's let X be a GIT. You can do this for any type of stability. Let's say polystable. Cubic surface. You can replace poly with semi, or I mean, whatever. I don't know. If you're going to prove this if you want to prove that the equality that I wrote above, you have to do this for poly, semi, and just regular stable. But we'll just do it in one case. Let this be a GIT polystable cubic surface. Then, by step 0, we can find a smoothing of X, maybe we'll call this curly X over some base, where the generic fiber is K stable. So this is by step 0, but the K stable version of step 0, which I haven't given you an example of. So we have some family where the generic fiber is K stable, but possibly not all fibers are K stable, possibly not X0 is K stable. So up to shrinking some neighborhoods, what we can do is use properness of K-moduli. So we have this X over T, where maybe we have this central fiber 0, which is my X, that we don't know if this is K stable or not, but we know, I guess maybe this is, what step are we on? Step 2. Step 2. We'll use properness of K-moduli. Is that there exists, even if the central fiber is K unstable, there exists, maybe up to a base change of T, there exists a family with central fiber that is K polystable. Okay? So there exists some X prime over T. T is possibly a base change of T, so this is terrible notation, but there exists some X prime over T where X prime above the central fiber is, in fact, just the same thing as X. but, and let's say central fiber x prime 0 is K polystable. Okay, so by properness of K-moduli, there certainly exists, I mean, even if x that I started with was K unstable, there exists a filling that is K stable, or K polystable. That's what properness tells me. This might be unstable, but I can find a possibly different central fiber that is K polystable. And now, what we want to do is use this. If we knew that x0 prime was a hypersurface, it would have to be GIT polystable by this theorem. But the GIT moduli space is separated. So now we'd have two GIT polystable limits of the same family, which must be the same. That's going to be the argument, but we don't a priori know that this is a hypersurface. Okay, so step 3, this is why we have to do step 3. We'll write down that in a second. But step 3 is prove that x0 prime is a cubic surface. Right? It still lives inside P3. A priori, it is a K polystable degeneration of cubic surfaces. So how do we do this? We use this volume bound over there. Okay? So how? Well, we know x0 prime is K polystable. So minus kx0 prime squared has to be less than or equal. Okay, well, okay, before I write that, let's say, so 1, it has quotient singularities. Because for surfaces, K semistability implies KLT, so it has quotient singularities. And if you have a quotient singularity, 0, something that looks like the origin in A2 mod a finite group, the normalized volume, I didn't tell you what the normalized volume is, but at least in this case, the normalized volume is n to the n divided by the size of the group. So in this case, it's 4 divided by the size of the group. Okay? And then 2, the volume bound over there, volume bound says that if it is K polystable, the volume, which is 3, right, because that's fixed in our moduli problem, the volume is 3, is less than or equal to 1 plus 1/2 squared times 4 over the size of the group. Right? So, you can write this as 3 over 2 squared, and the 4's will cancel. So 3 is less than or equal to 9 over the size of the group, which tells me the size of the group is at most 3. Right? Okay, so here we actually have to do arithmetic. But nonetheless, we get if x has quotient singularities, which it must because it's K polystable, then those singularities have index, or I guess not index, but the singularities are quotients by a group of size at least 3. We know what those are. There's not very many groups of size less than or equal to 3, right? So so this tells me if you have seen quotient singularities, you've seen this notation, but if not, let's say if you have a finite group or a cyclic group, right? Let's say, just as a notational aside, we use the notation 1 over n, 1a, to indicate the quotient singularity. I guess you could write AB, I don't know, AB, to indicate the quotient singularity that is A2 mod Zn, or I guess usually we should write mu n, where mu n acts, or a generator, a primitive nth root of unity, acts on the point xy by acting with weight A on x and weight B on y. Okay, so that's just the notation we use. So if you have a quotient singularity of this group of size 3, it has to either be one of the following. Okay? So in this case, our singularity A2 mod G must be either a 1/2 1, 1. By our quotient singularity, I mean, our quotient acts freely in codimension 1, so we can assume that both a and b are relatively prime to n. So it must be a 1/2, 1, 1, or a 1/3, 1, 2, or a 1/3, 1, 1 singularity, and those are the only options. Up to choosing a different primitive nth root of unity, this is the same as 1/3, 2, 2. This is, if you like the ADE notation, this is an A1 singularity, and this is an A2 singularity, and this is the cone over the twisted cubic. That's what singularity this is. But here's where we're actually almost done. Looks like we're doing some random calculation with singularities, but this is not smoothable, or not two-Orenstein smoothable. This is a theorem that you have to prove. Okay? But so this is not Q-Gorenstein smoothable. So in particular, it can't appear as the central fiber of this degeneration, right? Because we started with a smooth thing. So that doesn't show up. So we just have A1 and A2. And what's the crucial thing about this? Both of these singularities are Gorenstein. So this tells me that the canonical divisor of this x0 prime, this mysterious thing, is a line bundle. Because these are very mild singularities where that's still true. But then once you know this line bundle, you have to do some algebraic geometry, you have to do some birational geometry computations. The fact that that's a line bundle actually gives you an embedding of your x0 prime. So maybe I'll leave this as an exercise. This being a line bundle actually gives me a map, and the anti-canonical gives me an embedding from x0 prime into P3. This is not obvious, right? You have to prove it's base point free and prove the map is an embedding, and anyway, but you can do that. I believe you. I believe in you that you can do this. So you get an embedding, which tells you that this is a cubic surface. So now we're pretty much done. Now we're pretty much done because step 4, apply Paul-Etienne, which tells you that x0 prime is K-Pauli stable, and it's a cubic surface. So by the theorem that was just here that I just erased, x0 prime is GIT polystable. So like this was K polystable, and it's a cubic surface, so it's GIT polystable. And then the last step of this is GIT moduli is separated. And both x0 prime and the x that we started with, way back there, were limits of the same family, right? These families are isomorphic away from that central fiber. So our limits of same family, so they must be isomorphic. But x0 prime was K polystable. So that tells me that x originally was K polystable. So we did it. Okay. The crucial part of this proof that makes GIT equal to K stability is this part, that the central fiber of our degeneration was still a hypersurface in P3. And in fact, this exact argument is the structure of an argument that will work in higher dimensions. But you need, in higher dimensions, an understanding of this inequality. And if you are familiar with the so-called gap conjecture, if the gap conjecture was true, you would be able to essentially make this argument work in all dimensions. So this is known that GIT for cubics is the same as K stability for cubic surfaces, cubic 3-folds and cubic 4-folds, and it's conjectured in general, basically by this argument, but it relies on some technical thing about the normalized volume, which we don't know to be true. Yeah, it's only for cubic. It's false. I mean, this is false for not cubics. Yeah. Yeah, so for quartic hypersurfaces, this is false. GIT is not, I mean, for example, you can have like GIT semi-stable quartics, like you have non-reduced ones in there. So in particular, they can't be K semi-stable.
When in step 1 you wrote that the dynamic value is K stable.
Yeah.
You mean K fully stable?
So I mean, in this case, we can, by not what step 0 is written, but by picking a different surface, that you can assume the generic fiber is K stable. Yeah.
So in general, you would get, I mean, if you were using this in another argument, K fully stable.
You can, yeah, I mean, yeah, you can modify this argument suitably for other families, but this will only work for cubic surfaces. I mean, or cubic hypersurfaces, because in general, like we just know it's false that K, I mean, GIT stability of hypersurfaces does not imply K stability. Like it becomes false in degree 4, and then any other degree. So yeah, we don't know that. Yeah. Okay. Questions? Comments? Yeah.
So is there something known about the normalized volume for like terminal fields?
Yes. So so we know. So there's some conjecture. There's conjecture that's circling around here. We know that a smooth point always have normalized volume n to the n. That's always true. And then the conjecture is that there's some discreteness of this, and the next largest volume is the normalized volume of an ordinary double point, which is just some number, right? And so this is known in dimension 3. It's known to be true. So we know something about this, but it is not known in higher dimensions.
So if I give you a compound without similarity, do you know what the normalized volume is?
For threefolds, yeah, I think, yeah, we just, there's things you can look at, but for higher dimensions, we don't have a great understanding of this, I guess is what we're saying. But for threefolds, you can look at the list. I couldn't tell you what the answer is. I'd have to look at the list. More questions? Yeah. Yeah, so I mean, the GIT moduli space is an irreducible, I mean, it's irreducible. It's a quotient of this projective space of cubic surfaces. And yeah, so it's very nice. More questions? So this is sort of the general structure of an argument that one could take to approach showing the GIT of certain hypersurfaces, or maybe certain complete intersections, if you're interested in this, is the same as K stability. The problem is, in general, they're not usually the same. Okay, they're the same in this case, but in general, they're not usually the same. So you have to do something else. So maybe we have 15 minutes left. So I'll tell you, I guess, one other how you might use something like this to approach a more general moduli problem where GIT and K stability are not the same, but you can still leverage tools of GIT to understand K stability. Okay. So let's maybe clear, I don't know, bring the board down. Bring the board down. Right, so cubics, we understand. And the theorem, I didn't write this down, but this is originally by Odakas Body Sun for cubic surfaces. For cubic threefolds, it's Yu-Chen Liu and Chen-Yang Xu. And then for cubic fourfolds, it's a paper of Yu-Chen Liu. So these are known and conjectured in general. I mean, in fact, it is conjectured in general that every smooth hypersurface is K-stable. That's a conjecture. We don't know that, but that's true. That's a conjecture that people will say. So what do you do in the case where GIT is not the same as K stability? Well, it turns out, not always, but a fruitful perspective for many moduli spaces has been, or a fruitful perspective for many K-moduli problems has been to say K stability is not necessarily the same as GIT, but they're related. So in just one more, you can do this much more generally, but since we only have a few minutes, let's give you an example of how this might go. Well, let's say we just did cubics, so let's try degree 2 del Pezzos, see what happens. So let's look at the K-moduli of degree 2 del Pezzo surfaces. So surfaces where kx squared is 2. So fact, theorem, exercise, I don't know. I don't know what you know or what you don't know. A generic, okay, let's just say a smooth degree 2 del Pezzo surface, maybe X, is a 2-to-1 cover of P2 branched over a quartic. So you have some map, I don't know, C. So you have a 2-to-1 map from X to the projective plane, and the branch locus is a quartic curve. So why is this useful? What Tiago was talking about, the K-stability of this and the K-stability of this are very related, right? This is a finite group, so maybe the general theorem is by Zhuang, but then also I think this is earlier known by work of Liu and Xu that says X, K, poly, stable, or semi-stable, if and only if the pair P2 1/2 C is K, poly, or semi-stable. So in order to study the K-moduli space of X, it's essentially equivalent to study the K-moduli space of this pair. They're not literally going to be the same. I mean, somehow this stack will be like a mu2 gerb over this stack up to the covering, but close enough, ignoring some stack theoretic issues, the K-moduli space of this will be the K-moduli space of this. Okay? So to answer this question about K-moduli of degree 2 del Pezzos, we could ask, so we have this K-moduli space, M, I'll use the same notation, M smooth of volume 2, or dimension 2 and volume 2. This is just the smoothable component. So this is our K-moduli of degree 2 del Pezzo surfaces. And in some sense, you have to prove this. So I'll put equal in quotes, but this is equal to the K-moduli space. Maybe, I don't know, I don't have a good notation this, but M, I'll call it M K 4 upper 1/2. So what is this? This is going to be the K-moduli space of plane pairs P2 1/2 C, where C is a quartic, and their degenerations. Right? So, the generic fiber of this moduli space will be a pair like this. But, the del Pezzo could degenerate, so P2 might be able to degenerate. So this is something, but this is not the GIT moduli space of quartics. Okay? So you have some other space, MGIT4, which by what we were just doing, we were talking about GIT of hypersurfaces. So you could say GIT of quartic plane curves. And it turns out these are birational, but not isomorphic. A priori, there's not even a morphism between them. Okay? And one way to see this is what was being asked about earlier about hypersurfaces. There is a plane quartic curve. So if you take the double conic, xy minus z squared, this is a GIT polystable quartic, but this pair is not KLT. So, right, if you take this as your quartic, so it can't be K polystable, semi-stable. It can't be any of the K stables because that implies it would be KLT. So we know that this and this are not the same. But you may still want to relate the K stability of these pairs to the GIT stability because we know this. It turns out that the GIT of quartics is really quite well understood. And it is just a, I don't know, we can just draw a picture. We can draw a picture, oops. Sorry, I'm figuring out this board situation still. You think after almost 2 hours I would have that under control, but no. So the GIT of quartics, we understand. That would be the main reason we would want to relate this K-moduli space to the GIT of quartic. So we have a K-moduli space that maybe we want to know something about, and we have this GIT moduli space, MGIT of degree 4. You have some space that has some curve in it where one point is this double conic that we wrote down. So that's some polystable point in the GIT moduli space. And then the rest of this curve parameterizes quartic curves with tack nodes. So these aren't really, it's not really important what this means, but like if you take a conic, if you take two conics that are tangent at 2 points, that's an example of a curve with a tack node. So the point is we have a really good understanding of this, good understanding. We don't necessarily have a good understanding of the K-moduli space where the coefficient is 1/2. But what we do know, right, is that the same theorem of Paul and Tien, suitably understood, still says that K-stability of certain of these pairs, P2 1/2C, implies the GIT stability. That is still true. Okay, Paul and Tien still applies. K-stability will imply GIT stability of the quartic. I mean, if the ambient space is P2, right? If you're looking at a pair P2 comma curve, K-stability implies GIT stability. What happened in this cubic surface case, right? We said, oh, okay, if you have a GIT, some GIT polystable thing that's K unstable, find a limit and you can do this, all of this, but P2 is already K polystable, already. So what I guess one can show by pretty much the same argument that I'm currently erasing is that provided we look at moduli of pairs, but this coefficient of the curve is sufficiently small, GIT and K moduli are going to be the same. So the shift in perspective here that we want to make, which makes a lot of our moduli problems tractable, is consider K moduli spaces of pairs maybe x comma d, where x is something, and put a coefficient in front of the divisor. I mean, that's what we're trying to do with the 1/2 picture anyway. Right? Put a coefficient in front of the divisor where maybe at this point this is a rational number, and it's between 0 and 1. I guess strictly less than 1, so we have some KLT assumption here. The entire K-moduli theorem, even though we didn't discuss it last time, holds for pairs as well. Okay, just like we know how to do K-stability for pairs, so you can make K-moduli spaces of pairs. And so for each such C, okay, at least if the coefficient, or maybe let's say if, this is true in much more generality, but to be safe, I'm going to say if the divisor is Q-linearly equivalent to some multiple of the anti-canonical, so R is just another rational number. Like in the case your variety has Picard rank 1, this will be true. Then 1, I guess for every C, there exists some K-moduli space. Every C is setting up stack in space. It might be empty. I said there exists, but I mean, it might be empty. So maybe I'll call it M, I don't know, K, PS, but I'll just index it by the coefficient C and the moduli stack, the moduli stack and the moduli space indexed by the coefficient. But as you vary C, the moduli spaces start to vary. And so you have this well-behaved K-moduli stack / space, but if you change C, these stacks and these spaces vary with C, but in a very controlled way. Okay? So as C varies, there exists, maybe this is part 2, there exists some wall crossing, which just says, like, there exists a finite sequence of some numbers, C1, maybe up to Cn, where if you are in between any of these intervals, your K-moduli space, your K-stability condition doesn't change. Maybe C is isomorphic to the K-moduli space C prime for all C, C prime in the same interval. Okay. So as C varies, like a priori for every C you get a different moduli space. But actually you don't. For C in these neighborhoods, or these intervals between C1 and C2, you get isomorphic moduli spaces. And at one of the critical values, you have a diagram where you understand the, I mean, you can do this for the stacks too, but I'll just write it for the spaces because that's what we're going to use here. I guess the K polystable, if you're at some critical value Ci, and you subtract epsilon for some small epsilon, this has a map to the K polystable moduli space at the critical value Ci, which has a map from the K polystable moduli space on the other side. So there's some sort of birationality between these two spaces, but they admit some common birational model at the wall. Not necessarily. Not necessarily. It's possible that this is an isomorphism on one side and a divisorial contraction on the other. Yeah, I mean, yeah, it's going to come up in just in 1 second in the quartet case. Yeah, yeah. I mean, it turns out in the quartet case, if you're, this side is an isomorphism at the first wall, and this side is a blow-up. Yeah. So if you didn't understand the question, hold on. You'll see an application of this momentarily. But as you vary C, you get a wall-crossing framework that you get a moduli space for each C, but there are these sort of rational, these finite numbers that you have to pay attention to where the moduli space changes. But other than that finite number, I mean, they're all the same. And why does this help us? In the moduli problem at hand, maybe like a theorem, for coefficient sufficiently small, so so maybe think epsilon or something, the K moduli space of this coefficient C of pairs Pn and a divisor and degenerations. So in the setting of quartic, if the coefficient is very small, using a volume bound for the pair case, which exists, I only stated it here, if that coefficient is very small, then you just, essentially all this is detecting is the polystability of the ambient space. But Pn is already K polystable. So if the coefficient is arbitrarily small, any degeneration of this, it turns out the ambient space has to be a degeneration of Pn, but Pn is already polystable, so it must be itself. So the Paul and Tn argument tells you that this K moduli space for small coefficient is in fact isomorphic to the GIT moduli space of the divisor. I don't know, this is like terrible notation, but if you don't know what I mean, please ask. So this is this GIT construction that we were talking about before. So on the board at the very top, what that tells me is that our GIT moduli space of quartic curves is a K moduli space, but just for small coefficient. So I'm going to label that here. I'm going to bring the board down temporarily, but if you're still taking notes here, it'll come back in just a sec. But this is the same as a K moduli space of pairs for some coefficient. So this is pairs P2, some coefficient of the quartic, which I called C, I don't know, where, okay, this is why I didn't want to use C. C, whatever. Okay, where C is small. Okay, and so what we want by this G equivariant K stability, to understand the K moduli of del Pezzo surfaces, we want to understand what happens when we start with C very small and we try to increase C up to a half. So we want to do this wall crossing picture when we start, I don't know, close to 0, and we just want to go up until we hit 1/2. And if you can track those wall crossings, if you can track what's happening as the moduli spaces change, then you will get a complete description of the moduli space you want, which is this polystable thing with coefficient 1/2. And it turns out that you can just one can do this. Since we only have a minute left, maybe I'll just tell you the answer. I'll tell you the answer here. Oh, I'll just switch these boards. That's the right thing to do here. So, oops, wrong board. Okay, we're almost there. So by several different kind of delta-like computations, what you can show is that you don't actually even need delta. I mean, you can use log canonical thresholds, but for every curve in the GIT moduli space, except for this one, the associated pair is K-polystable for all C between 0 and 3/4, or how far you can go up to stay being log mono. Right? So you can do some computations to say, this is the only bad point in this moduli space. So if I have any wall crossings, they all have to be sort of centered at that point. Any place the moduli space change, because this is the only point that won't appear here. Everything else will appear here. And it turns out, back to Jesus' question, is if you do this wall crossing framework, you have this K moduli space, and this turns out to actually be a morphism, and you can blow up the point, I don't know, call this P. P, blow up P. This is, this is of some projective variety, and we can blow up a point, but what is important about this is that this, then this gives you some divisor, I don't know, right? So you still have some interesting curve, and then you have some divisor just from the blow up, but this ends up being exactly equal to the moduli space of these, I don't know, K semi-stable, K polystable pairs with coefficient 1/2, where the divisor, which I'll call E parameterizes. We can't parameterize curves on P2 because we already would have seen them here. Okay? So E parameterizes pairs of the weighted projective space, P114, and I don't know, a degree CD, where D is degree 8. So D is of the form, if this has coefficients x, y, z, z squared equals some polynomial in x and y. Where in fact, this is also some GIT problem, and that octic is a stable binary form. So what's really happening here is in the description of wall crossing, this moduli space, you have a wall. So there exists a wall at C equals 3/8. Using your knowledge of delta invariance, you could compute the delta invariant of just this divisor on P2. And it turns out that the pair is K, if the pair was going to be K polystable, the coefficient of that divisor would have to be less than or equal to 3/8, K semi-stable. So you can compute this number from this divisor. There exists a wall at C equals 3/8, and this is an example of what's going on in the previous case, but one of these two, typically, I don't know, this is sort of an unusual behavior, but typically, you have something interesting happening on the walls here. You have M 3/8 plus epsilon. Maybe this is your K polystable thing. You have a map to the K polystable moduli space at 3/8, and you have a map to the K polystable thing at 3/8 minus epsilon. And in this case, this is an isomorphism, and this is a blow up. So this is the wall crossing that's happening. But the point is, we have some space that we really understand. We can do a blow up. And in fact, if you work with the stacks, you actually do a blow up of the universal family, which is how you understand what the new universal family parameterizes. So you get to work on the stacks where you have a description of all these objects, do some birational geometry to the stack to say, oh, when I blow up this point, I get some other moduli space, but I know exactly what it is. And then you can prove that for every pair that appears in this moduli space, which a priori is at 3/8 plus epsilon, the next wall is not until 3/4. So when you get to 1/2, you're still in this chamber where you're between two walls. So this is the, I don't know, you get a moduli space of pairs where the ambient space is either P2 or P114, and you have appropriate curves on them. And then to complete the answer of the moduli space of degree 2 del Pezzos, you just take the appropriate double cover. And then you know. Then you know all the K polystable del Pezzo surfaces of degree 2. And so this kind of framework of starting with some moduli space that we understand and trying to get to some moduli space we don't understand, what we mean by wall crossing. And it's proven very useful in a lot of the K-moduli problems when we know we have some GIT place to start, because these are usually well understood, and then you can do all these wall crossings and find an interesting K-moduli space. So I will stop there, but if you have questions, I'm happy to answer. Thank you for listening.